Good morning, dear students. Today we do not have electricity at home, so I cannot take the class on Google Meet. So I have recorded this video for your class. So last time we have done the basic concepts in probability, and as a continuation, we will do one important theorem today. But before the theorem, we have two or three important terms that is required. That is number one, mutually exclusive. What is mutually exclusive events? Two events A and B are said to be mutually exclusive if they do not occur. This is they. If they do not occur simultaneously, meaning in terms of set notations, if A and B are mutually exclusive, are two events which are mutually exclusive, then A intersection B will be an empty set, that is phi. So there are many examples and you can think of. In general, events A1, A2, AM are said to be mutually exclusive if no two of them can occur simultaneously. Then the event A1 union A2 union AM means the occurrence of at least one of these events. So the meaning of A1 union A2 and A1 intersection A2 is that in the first case, that is A1 union A2, this is the event that at least one of the events A1 or A2 will occur. And A1 intersection A2 means that A1 either A1 will not happen or A2 will not happen. That means they cannot happen simultaneously. So that is the idea. So exhaustive events. The next is the exhaustive events. Events A1, A2, AM are called exhaustive if their union is equal to the whole sample space. Then it is called exhaustive events. So the theorem is, now if A1, A2, AM are mutually exclusive events, then probability of A1 union A2 union AM is equal to sum of their separate probabilities, that is PA1 plus PA2 plus PAM. Proof. It is simple proof. So as usual, we denote R to be the total number of elementary events in the sample space, and RAI is the number of elementary events favorable to AI. I is from 1 to up to M. Then the number of elementary events favorable to either A1 or A2 is RA1 plus RA2. Favorable to either A1 or A2 is sum of RA1 plus RA2. Now, probability of A1 union A2 by definition will be RA1 plus RA2. This is, what is this? As I have said in the beginning, probability of A1 union A2 means probability of occurring at least one of these two events, either A1 or A2. So we will take the number of elementary events favorable to either A1 or A2 is RA1 plus RA2 here divided by R, that is the total number of elementary events in the sample space. So by simplification, this is RA1 by R plus RA2 by R. This is equal to, by definition, PA1 plus PA2. So for only two events, the proof of the theorem is done. Now we can repeat the above concept and we get this. PA1 union A2 union AM is taking A1 to AM1 is one set and AM is another set. Then by the above, by equation number 1, it is plus. Now this union is plus. Note that this should be mutually exclusive events. Otherwise, the theorem cannot be proved. A1, A2, AM are mutually exclusive events, meaning A1 intersection A2 intersection AM is equal to the empty set phi. They are mutually exclusive. So P A1 here in this up to AM minus 1, again you break up probability up to AM minus 2, this would be capital A, union AM minus 1 plus AM. Here AM is as it is. This is equal to P A, again applying equation number 1, it is this union becomes plus. So we go on doing like this and ultimately we get PA1 plus PA2 plus PAM. So this is the proof. As a corollary to this theorem, again another point is incorporated to A1, A2, AM. Not only that, they are mutually exclusive, they are also exhaustive. Then PA1 plus PA2 plus PAM is equal to 1 because probability of the whole sample space is 1. Here probability of the whole sample space is 1, and the definition of exhaustive has been done as A1 union A2 union AM is equal to the whole sample space. So in particular, the events A and the A complement. This is the set event A, and AC is the complement of the set A. They are mutually exclusive. That means A intersection A complement is phi, and they are also exhaustive, means A union A complement is equal to the whole sample space. Therefore, PA plus PA complement will be equal to 1 by this. Thus, you know PA is equal to 1 minus PA complement. There are many examples we can think of regarding which will be A and which will be A complement. As for example, in the case of throwing of a dice, suppose A is 1, 2, 3, and then therefore A complement will be 4, 5, 6. So similarly, if you your PA is 3 by 6, that is half, and similarly probability of A complement is also half. So half plus half is 1, like that. Now in corollary to, suppose an event A is A1 union A2 union AM. A may not be necessarily the whole sample space. Suppose these M events constitute the event A, where A1, A2, AM are mutually exclusive, then PA is equal to PA1 plus PA2 plus PAM. This is just a particular case of the main theorem. As an example, suppose in a random throw of a dice, let A is equal to 1, 2, 3 and A1 is equal to 1, 2, A2 is equal to 3. So A1 union A2 will be 1, 2, 3, that is A. Then we see that A1 and A2 are mutually exclusive, that is A1 intersection A2 is phi, empty set, and also A is equal to A1 union A2, so that PA is equal to PA1 union A2 is equal to PA1 plus PA2. This is equal to PA1 is 2 by 6 and PA2 is 1 by 6. This is equal to, after addition, 3 by 6. This is equal to half. So we verify it. In fact, PA here 1, 2, 3, PA itself is 3 by 6 is equal to half. Corollary 3. Suppose two events A and B are such that A is a subset of B. A is a subset of B, is a set notation. Meaning thereby the occurrence of the event A implies the occurrence of the event B, but not the vice versa. Then events A and B minus A are mutually exclusive. In set notation, if A is a subset of B, then B minus A is those elements of B which are not in A. So this is B minus A, we write it as B minus A. And A intersection b minus a is equal to 5, meaning the events a and b minus a are mutually exclusive. Now b occurs if one of the mutually exclusive events a and the b minus a occurs. Therefore b is equal to a union b minus a, that we have already discussed earlier. By corollary 2, pb is equal to pa plus pb minus a. So this implies that pb minus a is equal to pb minus pa. By simplification, if pa comes here in this side. So for example, this result is very important, and see this example. A is equal to 1, 2, 3, b is equal to 1, 2, 3, 4. So now obviously a is subset of b. There is another element 4 which is not in a, and b minus a is equal to 4, and the a intersection b minus a will be 5. Therefore pb minus a is equal to pb minus pa. This is equal to 4 by 6 minus 3 by 6. pb is 4 by 6 and pa is 3 by 6. So this is equal to 1 by 6. So pb minus a is equal to 1 by 6. What is pb minus a? Will be b minus a is only 4. Therefore the probability pb minus a is 1 by 6. This is verified. So we have 11 minutes. I will upload the short video in YouTube, and you can watch it repeatedly, and if any difficulty arises you can also ask in the WhatsApp group, so that I will try to answer your questions. So this is for your elective class for today. So stay safe, stay home,